For our third example, we're going to use a tennis example, and we're going to talk about Venus Williams. So a tennis ball is traveling 10 meters per second and is returned by Venus Williams. It leaves her racket with a speed of 36 meters per second in the opposite direction from which it came. So there's a lot of important information there because this is when the skies method is really important, that we're drawing a picture to visualize. There are two parts to this problem. A, what is the change in momentum of the tennis ball? And B, apparently I stuttered when I typed there, BB, if the 0.06 kilogram ball is in contact with the racket for 0.02 seconds, with what average force has Venus hit the ball? So there's two parts. We want to know the change in momentum, and we want to know what force Venus used to hit the ball. So here we go. Here's our sketch, which is important. The sketch is going to show the ball is moving towards Venus. Okay, we have the ball moving towards Venus at 10 meters per second, its velocity. But then she swings the racket, and it elapsed time that racket touches the ball is for 0.02 seconds. That ball's mass is 0.06 kilograms, and it is returned with a velocity of 36. Notice my vectors, two different arrow directions, two different lengths of the arrows, which indicate the quantity, the numerical value of that velocity. So the velocity with which it's returned is greater. So we have two different directions here. Okay, so what are we given? Well, we're given initial velocity. And if you notice, I put that as a negative number because it's coming towards her. It's the opposite direction of which it's going to be returned. So the initial velocity is coming towards her. So relative to her, that's a negative velocity of negative 10 meters per second. Final velocity of the ball after she returns it is 36 meters per second. Mass, 0.06 kilograms. Elapsed time, 0.02. Okay, what are we looking for? We're looking for change in momentum, and we're looking for force of impulse. Okay, so there's two different things we need to do here. For part A, our equation, change of momentum is mass times change in velocity. So we are going to multiply the mass times initial final velocity versus initial velocity. Final versus initial. Okay. For part B, well, actually, let's stick with that first. So our first part, we're going to solve for change in momentum. That is the equation. Mass times final versus minus initial velocity. So we come down here and we plug and chug. Notice our final velocity is 36 meters per second. Our initial was negative 10. So when we subtract a negative, this is, middle school math, okay? Subtracting a negative is basically adding a positive, okay? So we end up with 0.06 kilograms times 46 meters per second, subtracting the negative, okay? When we multiply that out, we get 2.6 kilogram meter per second, and that is the change in momentum. So part A is solved. All our units were correct. We had no conversions to make. Going back to part B, looking for the force. Okay, now we have to bring in that change in velocity that we just solved for. Okay, right here, that change in velocity, we just solved for that here. We did the final versus initial, so we know it's 46. So we're going to plop that number right in there. This is where our elapsed time comes in. We didn't need it in the first part, but we need it here. It was given in the problem. So we go down. We have our initial equation. We set impulse equal to momentum change. In order to solve for force, we have to move time to the other side of the equation, so we divide. And when we plug and chug, we take our mass times that change in velocity, which is 46, and divide the entire thing by 0.02, and we get 140 kilogram meter per second squared, which becomes 140 newtons. And that is how we solve the Venus Williams problem.